terribly expensive. So, what does a light water reactor do? Well, the basic principle is shockingly simple. It heats up water using an artificial chain reaction. Nuclear fission releases several million times more energy than any chemical reaction could. Really heavy elements on the brink of stability, like uranium-235, get bombarded with neutrons. The neutron is absorbed, but the result is unstable. Most of the time, it immediately splits into fast-moving lighter elements, some additional free neutrons, and energy in the form of radiation. The radiation heats the surrounding water, while the neutrons repeat the process with other atoms, releasing more neutrons and radiation in a closely controlled chain reaction. Very different from the fast, destructive runaway reaction in an atomic bomb. In our light water reactor, a moderator is needed to control the neutron's energy. Simple, ordinary water does the job, which is very practical since water's used to drive the turbines anyway. The light water reactor became prevalent because it's simple and cheap. However, it's neither the safest, most efficient, nor technically elegant nuclear reactor. The renewed nuclear hype lasted barely a decade though. In 1979, the 3 Mile Island nuclear plant in Pennsylvania barely escaped a catastrophe when its core melted. In 1986, the Chernobyl catastrophe directly threatened Central Europe with a radioactive cloud, and in 2011, the drawn-out Fukushima disaster sparked new discussions and concerns. While in the 1980s, 218 new nuclear power reactors went live, their number and nuclear's global share of electricity production has stagnated since the end of the 80s. A computer is made up of very simple components doing very simple things, representing data, the means of processing it, and control mechanisms. Computer chips contain modules, which contain logic gates, which contain transistors. A transistor is the simplest form of a data processor in computers, basically a switch that can either block or open the way for information coming through. This information is made up of bits which can be set to either 0 or 1. Combinations of several bits are used to represent more complex information. Transistors are combined to create logic gates which still do very simple stuff. For example, an AND gate sends an output of 1 if all of its inputs are 1, and an output of 0 otherwise. Combinations of logic gates finally form meaningful modules, say for adding 2 numbers. Once you can add, you can also multiply, and once you can multiply, you can basically do anything. Since all basic operations are literally simpler than first-grade math, you can imagine a computer as a group of 7-year-olds answering really basic math questions. A large enough bunch of them could compute anything from astrophysics to Zelda. However, with parts getting tinier and tinier, quantum physics are making things tricky. In a nutshell, a transistor is just an electric switch. Electricity is electrons moving from one place to another, so a switch is a passage that can block electrons from moving in one direction. Today, a typical scale for transistors is 14 nanometers, which is about 8 times less than the HIV virus's diameter, and 500 times smaller. Logic gate gets a simple set of inputs and produces one definite output. A quantum gate manipulates an input of superpositions, rotates probabilities, and produces another superposition as its output. So a quantum computer sets up some qubits, applies quantum gates to entangle them and manipulate probabilities, and finally measures the outcome, collapsing superpositions to an actual sequence of zeros and ones. What this means is that you get the entire lot of calculations that are possible with your setup all done at the same time. Ultimately, you can only measure one of the results, and it will only probably be the one you want, so you may have to double-check and try again. But by cleverly exploiting superposition and entanglement, this can be exponentially more efficient than would ever be possible on a normal computer. So while quantum computers will probably not replace our home computers, in some areas they are vastly superior. One of them is database searching. To find something in a database, a normal computer may have to test every single one of its entries. Quantum algorithms need only the square root of that time, which for large databases is a huge difference. The most famous use of quantum computers is ruining IT security. Right now, your browsing, email and banking data is being kept secure by an encryption system in which you give everyone a public key to encode messages only you can decode. The problem is that this public key can actually be used to